Hello and welcome. Imagine this. You're the proud new owner of a 40-year-old TRS-80 color computer 2 with 64K of RAM. Who could ever need that much RAM? And the first thing you do is you fire it up and you say, print how much RAM I have. Expecting to see something like 64K, instead you see about half that. Why? Today we're going to talk about how the SAM assigns memory addresses to physical memory, and we're going to talk about why it looks like half of that memory is missing, and how you can control the SAM to get that memory back. To demonstrate, we're going to look at a sample app that draws a bunch of pictures on the high-resolution graphics screen, and then captures those frames and copies them up to that missing memory. Then it will animate through those frames, and you could look like it's moving, and what are you looking at? Get out of here. I'm the one who's talking. Look at me. My eyes are right here, buddy. And the cool thing is because those frames are in that missing memory, you have all of the original 32K of RAM for your code and your data and everything else. Who am I kidding? Low-res, high-res is mesmerizing. When you access memory, you access it by using an address. And on the 6809, you get to use any 16-bit number as your address. So that means the range of all possible addresses goes from 0 to FFFF. In decimal, that means you have from 0 to 65,535, which is a total of 65,536 possible numbers. But 65,536 is just 64 times 1024. It's 64K. So we actually have plenty of addresses. We have exactly the number of addresses we need to access all 64K RAM. So there is no problem. And if you believe that, then you're probably forgetting about the ROM. So the picture looks a little bit more like this. So you've got RAM and ROM, and RAM is assigned these numbers from 0 up to but not including 8,000, and then ROM is 8,000 and further up. So that means you really only have 32K for the RAM. And for the ROM, you've got 32K split up between the color basic ROM, the extended basic ROM, whatever cartridge might be plugged in. And at the top, you have a small amount dedicated to hardware registers. So if you saw my past videos on the video display generator and how you can control it, that was through hardware registers. So those are special interfaces onto the hardware directly that you get to access by using these addresses. Don't ask me about what's going on over here. I don't know. Seems like it's wasted. Seems like a lot of waste, and that offends my delicate sensibilities, but I can get over it. But this basically gives us the problem. We only have 32K of addresses that we can use to talk to RAM. But never fear, for the synchronous address multiplexer is here. This is a special chip that sits in the color computer that does a whole bunch of things. Typically, when you look at a computer, you think of the CPU as the heart of the machine. But you'd be hard-pressed to argue that the SAM isn't the heart of the color computer. The SAM coordinates how the CPU and the VDG can both access memory. The SAM acts as a clock. The SAM has a bunch of things that it does for us, and one of them is it helps us with this memory problem. When the CPU goes to access memory, it is not directly connected to that memory. So every time you do a load or a store from the 6809 and you use an address, that address first goes to the SAM, and then the SAM decides where that belongs in physical memory. So if we could find a way to control the SAM, we could control this mapping. And sure enough, there are 2 bits on the SAM that we get to control, the TY and the P1 that I'll talk about in a minute. But to understand that fully, we need to understand how physical memory is laid out. So it's split into 2 32K pages. Page 0 is the page you're used to seeing, and that's the one that's always there by default. Page 1 has been hidden from us for too long, but by controlling the TY and the P1, we get to change this mapping. We get to change how the SAM will return a piece of physical memory when an address is passed to it. The TY and the P1 are both just bits. They can either be set or they can be clear. Let's talk about the TY first. That's the memory map type. You set or clear it by writing to this address to set or this address to clear. This is very similar to how I discussed in the video display generator. You can control where the start of the screen buffer is by setting a bunch of different addresses, sometimes which acts as setting a flag or sometimes acts as clearing a flag. It doesn't matter what value you try to put in this address. All that matters is you try to write something to it, and that results either in a clear or in a set. Now, by default, TY is clear, and so that means the upper part of memory points to ROM and the lower part of memory points to RAM, as we saw. But if we were to set it, both the lower and the upper point to RAM. The P1 flag decides what happens in that lower half, these smaller addresses. By default, it's clear, and in the lower half, you see page 0. But if you set it, suddenly the lower half will point to page 1. So let's look at some illustrations. So by default, both TY and P1 are clear, and that means we have RAM in the lower half, and that is specifically page 0, and we've got ROM in the upper half. Now, if we were to set P1, suddenly the RAM in the lower half is actually page 1. So by setting this, you would suddenly be communicating with that lost half of memory. But there are serious dangers with trying to do this mode, and I'm going to talk about these at the end of the video. Now, on the other hand, if you set TY to 1 and you leave P1 at 0, now you've got both pages as RAM. So the lower half of the addresses look at page 0 of RAM, the upper half of addresses look at page 1 of RAM. And if you then set P1 as well, then it's just swapped. So now, for whatever reason, you get to have the lower half of addresses pointing at page 1 and the upper half of addresses pointing at page 0. I don't think this is very interesting. So what I'm going to be illustrating is this situation. I'm going to run the demo, and then I'm going to go over the code. So the idea is to draw about 5 frames, and then it will flip between those frames in an animation. So right now we're in this mode, so we get to use BASIC to do our drawing. But right now, very quickly, we flashed to this mode so that we could save that frame up into upper RAM. And then we flipped back to the ROM-RAM mode so we could start drawing the next frame. And so each frame, I'm just doing a little star field and then some wagon wheels, like combo of Western and science fiction, Oregon Trail in space. Because I can't draw, so I figure geometric things are the best that I can do. And so here you see we're flipping between the frames, and it looks like fairly smooth animation. And the star field is kind of like blinking. And the beauty of this is that we're not wasting any of our precious lower 32K of RAM. So that still remains available to us to hold whatever basic program, whatever assembly language code, whatever we need. We got all of that space still, and all of the frames are just stored in the upper RAM, which is normally neglected. The code consists of a basic part and a machine language part, so we're going to look at the basic first. When you run the basic code, it will load the machine language code, and then it will define 2 user functions that call into that assembly language code. So user 0, we call repeatedly for each frame. So when each frame is done being rendered, this simply copies it up into high RAM. And once we're all done with the frames, then we do the animation at the very end. So we just run this machine language routine to flip through all of those pages that we had copied. So we start by drawing. Everything happens on the 4:1 screen, P mode 4:1. And we're going to do 5 pages because that's really all we have room for in high RAM. If we were to use smaller pages, like for example, if we wanted to flip between text screens, that takes up a lot less space, and we'd have room for like 63 pages or so. But for high res, we have 5. So for each one, we clear the screen, we do our star field, so just random pixels throughout the screen, and then we do the 5 circles. So the one in the center has a radius of 50. These are the center X and Y, and then we call a subroutine to do the circle. And then we've got the 4 smaller circles in the corners. That circle subroutine draws the circle, and then it draws 10 spokes. And then we just use a little bit of trig to figure out where those spokes go. And once we finish drawing those 5 wagon wheels, that means we're done with the frame. So we can call that first machine language subroutine to copy the frame up into high RAM. That subroutine expects a parameter, the page number, and the page number it will use to calculate what range of memory up in high RAM to copy the frame to. And that's the end of the page. So when we're done, we just go back up and we do the next page. Finally, when we're done, then we call user 1, and that does the animation. And then this just keeps looping infinitely. So the real fun happens in assembly language. So let's take a look at these 2 routines and see how they work. At the very top, I have 2 jumps. So the idea is the first routine that BASIC can call will start at a known address, 4000, and then that just jumps to wherever the store routine lives. The second routine has a known start address of 4003, and that just jumps to wherever the animate routine lives. The reason I do these jumps is because it allows me to modify the code here however I like, but these addresses never change. And that way I can make changes down here with impunity and not have to worry about changing the basic code as addresses move around. So let's take a look at that very first routine. This is the one that copies whatever is in the graphics buffer up into high RAM. So these are the pages that we have access to in high RAM. So starting at hex 8000, and then since they're 1800 bytes long, these are the next pages. And then after this, we just don't have room for another page. First, we ask BASIC for the argument that was passed, and you'll see the argument represents the page number. So the page number will be somewhere from 0 to 4. Now we're about to flip temporarily into all RAM mode, so we're going to get rid of the ROM. That means we better not have an interrupt, because if an interrupt occurs, it's going to go through the interrupt vector, and then it's going to call into ROM, and ROM ain't there, so it's just going to call into whatever's sitting at high RAM at that same address, and terrible things will happen. So we save the original value of the condition code register, and then we disable the FERC and the ERC, the fast interrupt and the regular interrupt. And this magic instruction is all we need to flip out the ROM and to swap in the high RAM. So high is RAM is simply that address on the SAM. This is what sets that TY bit. If we look at the effect of executing this in the debugger, you'll see right now we're sitting just before we've done the store into high as RAM. And take a look at the memory. So right now I have the window focused at hex 8000, so we're looking at the beginning of ROM. In fact, you can even see the copyright here, extended color basic 1.1 copyright. Blah, blah, blah. Okay, so I'm going to do one step. So I'm going to step over this, but keep your eye on the memory window. Boom! It's RAM! You're looking at RAM. So in one instant, the SAM switched what address 8000 and on point to. It don't point to the ROM no more. It points to the high RAM. Next up, we take this argument that's sitting in the D register, but really the B register because it's only 8 bits long. And we do a little bit of math to figure out what page that relates to. That way, if it's 0, we're talking 8000. And if it's 1, we're talking 9800. If it's 2, 8000, and so on. And then when that math is done, we store the address into memory, into these 2 bytes here. And we begin our loop. So X starts where the graphics start normally, which is E100. U points to wherever the destination buffer lives, and we just loop and do 2 bytes at a time. When we're all done, we reinstate the ROM, we reinstate the condition code register, and we get out of there. Now let's take a look at the second routine, the animate routine. This does the flipbook style animation where it just flips between 8000, 9800, and so on, and then when it's done, it just cycles back to the beginning, and it just keeps doing this forever. We're going to do the flip coordinating with the field sync interrupt. This way we're not going to do a flip when we're in the middle of rendering the screen. So to start with, we do a P mode 4, color set 1. We go ahead and disable interrupts for now so that we can ensure that horizontal sync stays disabled from the PIA and field sync gets enabled in the PIA. This is probably unnecessary because BASIC does this already, but it's not too bad to be thorough. And you've seen this code before in the interrupts video, which you may want to give a look if you haven't yet and you're curious how all this stuff works. And once we're done setting up the interrupts, then we can begin. So this again is our magic store to flip out the ROM and swap in the RAM. And all of our pages should now be here. The A register will represent which page that we're displaying, so it's going to cycle between 0 through 4. And we're going to take advantage of a table that tells us which SAM bits I need to flip or flop in order to change the VDG start address to that particular graphics page. So this is that table. If you're curious to learn more about changing the start address of the VDG, you can check out this video. But the quick summary is that for each start address, you either set an even or an odd address to either set or reset a bit in a series of bits that end up identifying that start page. So each of these lines of addresses will identify a given start address that the VDG should use out of RAM. So for example, if I were to store an arbitrary value into each of these addresses, that would cause the VDG to flip to start address B1000, which would be the third of the 5 pages that we have ready to go. So we do a little bit of math to convert A, which ranges from 0 to 4, into an index into that table. And by the time we're done, X is pointing right at the start of the proper entry of that table. And U is going to represent a counter to help us slow down the animation. In fact, when I'm done, I'm going to show you what happens if I don't slow down the animation. But I'm going to let U range from 0 up until 5. And each of those happens on a field sync. So we're going to skip a field sync, skip a field sync, skip a field sync, skip a field sync, until finally we get up to 5. And then I'm going to change the VDG to point to the new start address. Field syncs happen 60 times a second. So we're going to skip over 5 field syncs out of 60 per second. So we render a frame every 1/12 of a second, which is still very fast, but not so fast that the motion seems too frenetic and wild to watch. And you'll see I'm using the sync instruction. I'm not actually using an interrupt handler. You can check out this video where I first introduced that sync instruction. It's just a very lightweight way of asking the 6809 to block, to stay, to wait until that next interrupt happens, and then it gets released and it continues on to the next instruction. And I can do that without needing to actually respond to the interrupt with a handler. So once we're on the field sync, that will have us change the start address. And now that X is pointing at the beginning of the entry of all those addresses that I need to write to, I just do the writes and realize that A, it doesn't matter what's in A, as long as we write something to these magic addresses, that will cause the start address of the VDG to change. So it'll now be pointing to whatever is the current page that we're supposed to be showing in the animation. When we're all done, we reset the counter that skips field syncs. We increment the counter that tells us which page we're supposed to be showing. We wrap around that counter. Once we hit 5, we wrap around it back to 0. And then we just go back up to the top of the loop. That's the whole thing. So just in case you're curious, how fast can this really go? So if I remove this code that skips every 5 field sync and actually renders the next page on every field sync, what would it look like? So as a reminder, this is what it looks like when we skip every 5 field syncs before going on to the next page. And if we don't skip, that's pretty fast. It's kind of wild to think that this is 40-year-old hardware. If you look at the stars, you don't even see them separated into individual frames. You basically see all frames at once, and they're just like blinking. And it looks like I'm in the high-speed turbo mode of XRoar, but I'm not. This is the actual normal speed. So that just leaves one thing to wrap up. When I mentioned this mode, where you have ROM at the top and RAM at the bottom, but you use page 1 instead of page 0, I said this was dangerous. In fact, I wanted to demonstrate this. In Topolt's assembly language programming for the color computer, he had a really interesting point. He talked about that P1 bit, and he indicated that if you set and reset that bit, that gives you the equivalent of having 2 basic programs in RAM at the same time, one in page 0 and one on page 1. So right now we're looking at program 0, now we're looking at program 1, now we're looking at program 0, now we're looking at program 1. I wanted to do a demo of this because it would be kind of cool if you ran the assembly language routine and then like did a list and all of a sudden, boop, different program. When I started to think it through though, I decided that it was more than I felt like doing. There were too many dangers. So the crux of it is, if you have ROM up here and the purpose is that you want to continue running the basic interpreter, you got to remember the basic interpreter is a program just like any other program. It has variables just like any other program. It uses state just like any other program, and all of that stuff lives here. For example, there are a bunch of variables here starting at hex 600 for disk basic. And before them, you have a whole bunch of variables used by color basic, used by extended color basic. You also have the interrupt vectors, and the ROM has special code in it to initialize and maintain all of these variables. The first time you swap in page 1, none of that stuff has been initialized, and BASIC is going to immediately crash. So you've got to do some work to go into here and initialize those variables and maintain them if necessary as you make changes. And let's not forget about the stack. As you swap back and forth, the stack completely changes. So if your code is in the middle of using the stack, if it pushed, if it popped, or whatever, you may need to copy some stack information along with you. And let's not forget your program itself, your assembly language program that does that swapping, is in RAM. So the very first time you go from here to here, you had better first have copied over yourself into the new page. So there's no doubt it could be done. In fact, I'm sure it has been done. There probably are products that allow you to switch back and forth and keep 2 programs in memory at once. But it was just more than I wanted to bite off. Well, that wraps up this video on 64K. All the code that you saw here you can download for free. There's a link in the description so you can try it out yourself and perhaps modify it for your own purposes. As always, thank you for watching.